Good morning, good evening, panel. This is Rajkumar, and here I'm presenting on abusive language detection on social media for my master's in machine learning and artificial intelligence at Liverpool John Moores University. Let's begin with introduction. So the history of abusive language goes way back to the rise of social media, even to the rise of email era. As we know that whatever we are doing right now on social media, it started with our work on emails. In the modern day time, as time progresses, we are moving into a digital era, and now we have seen that internet has joined the three basic necessities. And as we know, the Gen Z kids are so addicted to internet and social media that they can live without food for a day, but not the internet or social media. And with the rise of the internet, we see the rise of internet crimes, abusiveness, bullying, and hate speech has all covered over the internet. And this is what we want to stop. This is what we want to stop so that our children should not get it, learn this before the time. So as we know, the internet, social media was made as a channel for communication, for expertise, experiences, and to share the feelings. But it becomes a serious issue when these channels are used to spread sexism, racism, abusive language, and bullying. And this is the core of this research that we need to stop this. And machine learning can be our greatest weapon in this battle. Let's go with the problem statement. As we know, the text classification and abusive language detection are not something new, and there have been involving several monologue operations onto it. Abusive language detection is a difficult task and requires a lot of machine learning and pattern recognition algorithm. But this is not the case. The detection is not always accurate, and sometimes it can result into a false positive, and which leads us to many challenging situations such as written slang, sarcasm, screaming, and many other problems. Specific items are designated as offensive as they are intended to be defamatory, humiliating, or insulting. In contrast to assaulting text, abusive material is typically targeted towards social classes such as gender, religious, handicap, sexual orientation, or towards ethnic group. The majority of these methods rely on pre-trained text classification and models. There have been great research done on this topic on the English language, but there are very few. And recently, people have started doing research on abusive language on other than English language, which are Greek, Arabic, Dutch, Danish, French, Portuguese, Italian, Turkish, Slovenian, in Hindi, and other documents, which can help us to narrow down on our further research. Let's look at some literature review, some people who have done in this field. And in 2016, Nobada and Silva, to prevent the use of abusive language on social media, companies have standard guidelines that every user must adhere to, as well as using human editors in coupling with technologies that leverage blacklist, a regular expression to detect and eliminate inappropriate posts. As individuals increasingly converse online, the demand for high quality abusive language classifier abusive classifier grows rapidly. Abusive language detection can be quite dramatic and fair. Like in a common sense, we know that abusive language doesn't have to be obvious, but that's not the case because in sorry Nobata has also discovered that abusive language can be quite dramatic and fluent. There are numerous occasions where I have also mentioned some of the words like add another Jew, find a bison for stealing my tiny grab, hang them all. And I'm amazed that they reported on this nonsense. Who cares about another dead nigger? I mean, these are the slangs or sarcasm. These have used in abusive language, and these are quite fluent and quite grammatical. So let's look at some work that people have done on English language, and then we'll move on to the work that people have done in non-English language. So in 2017, Davidson, to separate the hate speech from other instances of objectionable language, is to significant difficulty for automatic hate speech detection on social media. Lexical detection approaches poor accuracy since They identify all communication containing certain phrases as hate speech. And earlier work employing supervised learning failed to differentiate between the two classifications. So Davidson gathered tweets containing hate speech term using a crowdsourced hate speech lexicon. Davidson employed crowdsourcing to classify a sample of these tweets into three categories. One was hate speech, second was offensive language, and third was neither. Davidson trained multi-class classifier to differentiate between these various groupings. A closer inspection of the prediction model and mistakes reveals when they can constantly distinguish hate speech from other offensive words. And when this distinction is more difficult, they discover that racist and homophobic tweets are more likely to be labeled as hate speech, but sexist tweets are more likely to be classified as offensive. Tweets that lack clear hateful words are likewise more difficult to categorize. For online, sorry, yeah. For online social media, abusive language identification is a challenging but a crucial job. The study contrasts a two-step techniques for conducting classification on abusive language and then classifying it into particular categories, with one-step procedure of completing a single meticulous classification for identifying sexist and racist language, with a public English Twitter corpus of 20,000 tweets including sexism and racism. So Park and Fung in 2017 did this research, and their technique achieves the promising F measure of 0.827 using hybrid CNN in one step and 0.824 using logistic regression in two phases. Now, Wasim in 2017 did another research and on abusive language reduction and evaluation expands. There is an increasing need for crucial examination of links between the many subcomponents that have been classified under the term abusive language. Based on their research on hate speech, cyberbullying, and online abuse, they suggested a topology that reflects the key similarities and distinctions across subcomponents and addresses the subsequences of data annotation and characteristics generation. They stress the practical steps that scholars may take to a better approach in the abusive language detection subtask. Now, Zhang and others in 2018 studies described a new strategy that is based on deep neural network that combines convolution and gated recurrent network. They conducted a thorough assessment of the method against many of the benchmark and state-of-the-art on the biggest collection of publicly released studio dataset, demonstrating that, especially in comparison to reported earlier results on these datasets, their suggested technique is capable of capturing both word sequence and other information in short text. Now, Zemperi and others in 2019 results and key conclusion of they found that in SEM-Eval 2019 task 6 on recognizing and categorizing offensive language in social media was presented by them. The project was based on the offensive language identification dataset, a new dataset containing around 14,000 English tweets and 3 subcomponents. The purpose of subcomponent A was to distinguish between offensive and non-offensive posting. The focus of subcomponent B was on the type of offensive content in the online post. And under subcomponent C, system had to identify the intended recipient of the offending post. Now, Paula Fortuna and others in 2021 did a substantial corpus of research on the automated detection, hate speech, and associated issues. Now, they use cross dataset model generalization. On the other hand, remain a difficulty. Throughout this setting, they discussed two unanswered critical questions. First one was, to what degree does generalization rely solely on the model and the composition and annotation of the training data in terms of different categories? And the second was, do particular feature of dataset or model impact generalization possibilities? To answer first, they conducted intra and cross dataset experiments with BERT and Albert FastText and SVM model trained on 9 standard public English datasets with standardized and comparable The test revealed that generalization differs between models and the some categories, for example, toxic, abusive, or offensive, work better as cross dataset training categorized than others, for example, hatred. To respond second question, they employed a random forest model to evaluate the importance of various models and dataset variables in pretending the performance of 450 BERT and 450 Albert, 450 faster, and 348 SVM binary abusive language classifier, which was in 1698 in total. They discovered that in order to generalize effectively, a model must first perform well within an intra-data set. Furthermore, several other characteristics, including the training and goal categories, as well as the fraction of out-of-domain vocabulary, are similarly important for the success of generalization. In 2022, Song and others found that the fast growth of online social media abusive language detection has become a trending topic in the area of effective computing. However, ALE approaches in social network ignores the interaction link between user posting, instead using ALE as a challenge of text context representation learning. To address this issue, they suggested a pipeline method that considers both the scope of the post and the feature of the interaction network within which it is published. So their technique is to split two components, pre-training and downstream tasks. To begin this, they employ bidirectional encoder representation from transform, which is a BERT model, as an encoder to construct phase reconstruction in order to capture subtle contextual characteristics of the posting. Later, they construct a relation special network utilization the semantic relation of post and the structural information from the interaction network. Upon that premise, they develop a special relational graph of neural network, which is RSGNN, to effectively deliver information in the interaction network and learn text categorization. Their experiment shows that their strategy can significantly enhance identification of abusive posts across three public data sets. The results indicate that introducing interaction network structure into the abusive language detection that improves detection output considerably. Now let us discuss some work that have been done in non-English language. So in 2022, in 2020, Jha and others, according to the number of speakers worldwide, discovered that Hindi is the third most, in 2022, Jha and others discovered that Hindi is the third most spoken language in the world. It has spoken by millions of Indians and has grown in complexity and usage as a result of varied geographical impact and linguistic preferences, while English, which is Hindi written in Roman script rather than the original Devanagari script, is widely used on the internet. That is true. That is what we use in our day-to-day language as being an Indian. So the number of native Hindi speakers written in Devanagari is increasing. Despite this, there have been very few studies conducted on the usage of Hindi as an internet language. The study proposes a methodology that uses a fast text-based model to differentiate and categorize abusive text from non-offensive text. The algorithm was able to categorize text from a dataset of Devanagari Hindi offensive text, which is also a DHOT. A great search strategy was used to modify hyperparameter state during FastTech, which revealed intriguing insights into model accuracy and precision. Their FastText model obtained 92.2% accuracy when processed on a desktop class computer. To the best of their knowledge, this is the first attempt to create a cutting-edge categorization of abusive language in Hindi utilizing FastText model. Sharma and others in 2020 proposed study focusing on analyzing hate speech in coded switch Hindi-English dialect. They investigate transformation strategies in order to obtain accurate text presentation. They created MOH, meaning map only Hindi. The MOH pipeline includes language recognition, Roman to Devanagari Hindi transliteration, utilizing a knowledge base of Roman Hindi terms. And lastly, they fine-tune multilingual BERT and MURIL, which is multilingual representation for Indian languages model. They perform many quantitative trials investigation on the three dataset measuring performance with precision, recall, and F1 score. The first trial compares the performance of MOH map text with standard machine learning models and find an average gain of 30% in F1 scores. The second measures the proposed work score against those of the baseline methods and find a 6% performance improvement. Finally, utilizing the current transliteration library, the third evaluates the suggested MOH approach to various data simulation. MOH surpasses the others by 15% in this case. Code mixing is a prevalent occurrence in social media writing, especially in multilingual nations like India. Traditional deep learning approaches learned on monolingual data do not work well enough on code mixed data, and training the new model is difficult owing to resource constraints. Transforming multilingual data to monolingual is a critical solution to this problem. In this paper, TIF-DNN, a transformer-based interpretation and feature extraction model, is suggested for each speech classification. In the proposed model, they employ the Indic NLP and English to Hindi library for transliteration and translation respectively, and MBERT for feature extraction. In 2022, L. Alami and others suggested research that will use transfer learning model and fine-tune phase to handle the multilingual offensive language detection challenge, which is MOLD. They propose an efficient method based on bidirectional encoder representation from transformer, which is BERT, which have demonstrated tremendous promise in collecting semantics and textual information inside text. The suggested method is divided into three categories. One is pre-process, second, text representation using BERT model, and third, classification into two groups, offensive and non-offensive. To deal with multilingualism, they investigated several studies such as joint multilingual and translation-based ones. The first is to create a single categorization system for all languages, and second is to translate all writing into a single global language and then categorize them. They ran numerous tests on multilingual data set derived from the semi-supervised offensive language identification data. The experimental result revealed that the translation-based techniques combined with Arabic BERT or Arab BERT obtain an F1 score of 93% and an accuracy of over 91%, which was awesome. So let's get into a research methodology that I use in this research for a abusive language detection on social media. So the data set description is the first one. So we have used the Twitter English data set for David's, which is also known as Davidson data set, which can be found in the papers of automated hate speech detection and problem of offensive language data set ICWSM 2017. So this dataset contains of 24,783 tweets, and also each tweet is either hate speech or abusive language or neither, as voted by the Crowdflower users. So the dataset contains on 5 columns, which is count, which tells the amount of individuals that coded each tweet as, each tweet on Crowdflower. Hate speech is the another feature that tells us like out of how many CF Crowdflower users have voted the tweet as hate speech. Offensive language is another feature which again tells us that how many users of CF has marked the tweet as offensive language, and then there is a neither, which tells us that how many CF users have voted this tweet to be neither offensive it's neither offensive nor non-offensive or hate speech. And then we have a class that will tell us according to the vote that this particular tweet is either hate speech or offensive language or neither. So in the data pre-processing, we did missing value treatment, we did feature selection, we did text cleaning, tokenization, normalization, and handle imbalanced data. Now to modeling, we did all these procedures and we did pre-processing, we did data. Sorry, in modeling, the first and foremost task was to gather data and do some pre-processing, which was we discussed in the last slide, which was missing value treatment, feature selection, explaining tokenization, normalization, and handling imbalanced data. Now, once we know that our data is ready to be fed to our models, we then started doing modeling on our data and training the model on the data and then evaluating according to it. I'm sorry, predicting first and then evaluating according to it. So once the prediction was done, we were ready to evaluate the model. So to evaluate the model, as we know that we need to know the which model is more effective than the other model. So for that, we had an evaluation metrics, and the metrics evaluation metrics were accuracy, precision, recall, and F1 score. Now, this is the result we found out that logistic regression in a so logistic regression was our go-to model, was our first model we did our training and evaluation. So logistic regression gave us accuracy of 90.38%, while precision of 75.17% and recall of 69.92%, with F1 score of 70.94%. Now, logistic regression, after this, we did logistic regression by undersampling the data, which gave us a result of accuracy of 80.3%, precision of 80.04%, recall of 80.3%, and F1 score of 80.04%. Now, after undersampling, we oversampled the data and tested with logistic regression. This time we got a better result than the past two occurrences, and we got accuracy of 90.65%, precision of 90.62%, recall of 90.65%, and F1 score of 90.6%. Now, we also tested logistic regression with TF-IDF vectorization. So with TF-IDF vectorization, we found out that logistic regression gave us an accuracy of 89.13%, precision of 89.09%, recall of 89.13%, and F1 score of 89.07%. So now we have found out that oversampling worked better than undersampling. And so we did what we did, we took oversample data and fed it to all of the models. While simultaneously, we also converted the oversampling data to TF-IDF vector and saw the result. So we moved on to naive Bayes with the oversample data, and we found out that naive Bayes gave us accuracy of 84.34%, precision of 84.48%, recall of 84.34%, and F1 score of 84.36%. Now we took the same oversample data and converted it to TF-IDF and fed to naive Bayes and saw the performance was, it gave us accuracy of 83.32%, 83.32%, precision of 83.43%, recall of 83.32%, and F1 score of 83.35%. Support vector machine performed, we can see that support vector machine performed way better than any of them, which gave us the accuracy of 91.45%, precision of 91.49%, recall of 91.45%, and F1 score of 91.41%. With TF-IDF vectorization, we found out the support vector machine gave us the accuracy of 90.36%, precision of 90.4%, and recall of 90.36%, and F1 score of 90.3%. Now, once we are done with this models, we wanted to go on ensemble method. So we tried random forest and XGBoost. So random forest with the oversample data gave us the accuracy of 80.47%, precision of 81.22%, recall of 80.47%, and F1 score of 7.81%. Now random forest with TF-IDF vectorization gave us accuracy of 40.79%, precision of 71.92%, recall of 40.79%, and F1 score of 31.09%. Now XGBoost was the final model we did in our research. So Our findings were that XGBoost with oversampling data gave us 87.32% of accuracy, 87.28% of precision, and recall of 87.32%, and F1 score of 87.16%. Now, XGBoost with TF-IDF vectorization of the same oversampling data gave us accuracy of 41.72%, precision of 69.12%, recall 41.72%, and F1 score of 32.68%. Now let's move on to conclusion and feature work. Now we found out that support vector machine perform way better than any other models we tried. And logistic regression, which is known to take up a low resources, perform just slightly behind it. And to counter imbalanced data, we found out that oversampling worked better than undersampling, and we tested with TF-IDF transformation, and we saw that ensemble methods called random forest or XGBoost with TF-IDF data, they perform very worst. Now, what can be said for future works? Yes, that in the study we use logistic regression, naive Bayes support vector machine classifier, random forest classifier, and XGBoost classifier. So we didn't use any Hugging Face bot model or deep learning models. So there is a clear opportunity to use these models and see how well they can perform. And as we know that the abusive language detection is an ever evolving field, so we need to keep on doing and testing with the new data set and testing on newer models to see how well they perform on a newer data set. So these were the references where I used in this PPT. And finally, thank you panel for being with me. This was my presentation. Signing off, goodbye. Thank you. Bye-bye.